Okay, so hello everyone, this is Akshay here, and let us continue the today's GFG period streak. And today's question is a good question, yeah. So there are several. If you have read this question, you must be seeing that there is bunch of information given here, right? And we need to observe this information, make something within it, and then we need to proceed on with the question. So let me just first plug in my charger. Okay, so sit tight and try to listen to each and everything, try to understand each and everything, and then only we together will be able to code the solution and understand it as well. So we have a Euclidean path here. So what it says is that it is a path in the graph that visits every node exactly once, right? And it starts and ends up with a different index. Okay. And then the another definition is Euclidean circuit. So Euclidean circuit is an Euclidean path which starts and ends on the same vertex. So that means one condition is common in both. Uh, that is that is we the that visits each every edge exactly once, correct? Okay, so that's the common thing in both the definition, path and circuit. We have been given undirected acyclic graph with v nodes e edges with the adjacency list. Return 2 if the graph contains Euclidean circuit and 1 if path, and otherwise return 0. ठीक है, बहुत सारे cases हैं. We need to first understand all the cases, that when and where these definitions will apply, right? So again, try to listen it carefully. So let's just write down our need. Once we have our plan in on a paper, then we can visualize more clearly. So first of all, it is saying that you have a EP, Euclidean path, and the definition they are saying is that you should visit exactly each edge once. Visit exactly each edge once, right? Can we comment something on this definition? Can we say something on our graph that it should look like something like that using this definition? So we need to visit exactly each edge once, right? So let us draw a graph here. Let us draw a graph here. So let us take the example from the given vertex test cases. So in the EP, we need to return 1, right? So the return type here is 1, let's say. So I am circling it. So the return type is 1. And you can see the graph as 0, 1, and 2, and it is following a Euclidean circuit. That's a 1 returns path, right? Contains a Euclidean path returns 1. ठीक है, यहाँ गलत लिखा हुआ है यार. It is not path. It is path, not circuit, right? Because circuit में इन्होंने कहा है कि you need to the starting and index should be even. So this is your circuit. The above test case, this is not, right? So 1, 0 and 2, ठीक है. तो अगर मैं 0 से स्टार्ट करता यार चलना, राइट, तो मैं क्या करता अगर, हाँ, सबसे पहली बात प्री रेक्विजिट्स DFS आप पढ़ के आना यार. हाँ, मैंने वीडियो बना रखा है. द वीडियो इज देयर ऑन DFS ऑन द ग्राफ second or third video. You must watch, then only you will be able to understand this question, because here I will not tell you how the DFS works. Again, coming back to the question, so if you start the DFS from 0, right, then what will happen, that you will go to its immediate neighbor, let's say 1. So I will go to 1, right, and then what will happen, the one will have no neighbors, and it will track back to 0. And then the another neighbor present here is 2, so it will look for, are there any neighbors left for 1? Yes, so it will say yes, you have a 2 here, right? So go back. So again, call the DFS for the remaining neighbors, that is 2. Again, 2 has no neighbors, so it will return back. Now if you see how many times you have visited 0, I would say 3 times. Once you started from 0, this is V1, then you track back from 1, so this would be your V2, and then you track back from 2, this would be your V3. This is not the question want that you exactly need to visit just once, right? And that is why they have given the traversal as start from 1, right, then go to 0, and then go to 2, right? So this is a directed edge. First of all, this is not a directed edge, this is a undirected edge, right? Okay, so they are saying that instead of going from 0, 1, instead of following the path 0, 1, 0, 2 and 0, you go in this path 1, 0, 2, and that's it. You'll be covering all the elements in your DFS, right? ठीक है यार. तो इसका क्या मतलब है कि अगर हमारे पास कोई ग्राफ होता 0, 1 and 2 and another let's say as 3, then what would happen if I called DFS from 0? Then what would happen? Or let's say if I have called 0 DFS from 1, because 0 से तो आंसर नहीं आने वाला है, तो मैं 1 से कॉल करता, 1 से 0 पे जाता, 0 से 2 पे आता, राइट? अब 2 के पास कोई नेबर्स नहीं है, right? But I know that the graph is disconnected here and there is 3. So it will again track back to 0, it will again track back to 1, and then the recursive call will be finished and it would call for 3. So again, note, if you are not able to understand what I said, what I did in the last 2 to 3 minutes, then it is highly because you do not know how a DFS work. तो आप इसको देख के आओ यार. That's why I said this question is a good question. There will be multiple things to say and understand for you guys. Okay, so that is why. So what is the observation we have made? That if it is disconnected, तब तो हमारा आंसर आने ही नहीं वाला है. नॉट पॉसिबल, आंसर ही नहीं आएगा. सो दिस इज द केस where you fall into an otherwise case, and otherwise it says to return 0 if you say here, otherwise return 0, right? So here EP or EC both would not be possible, right? अगर EP नहीं, if EP is not possible, then definitely EP is connected to EC, so EC भी नहीं होगा, right? In that case, he will return 0. So the first observation we just made is that to follow this criteria, that visit exactly each edge once, first you need a connected graph, and that's not it. We can see that 0, 1 and 2 were connected, but even if I start from 0, then you will get a traversal like this. But if you started from 1, then definitely you would have got all the vertices by visiting exactly once, right? So connected, so first of all you need to see connected, and then we also need to see that exactly once criteria, from which node we need to follow that, right? Okay, so these are the two things we need to handle. First of all, you need to check if it is connected or not. So simply हम इसके लिए से DFS function call कर लेंगे, and we will get that, right? But that is not, again, सिर्फ connected से काम नहीं चलेगा, हमें ये भी श्योर करना होगा कि हम किस नोड से ट्रैवर्स करें. That is to make sure it is exactly once, right? ठीक है यार. So now we have second definition. Where we need to return true. So I'm again circling it, and the second definition is about the Euclidean circuit. And one more thing that was mentioned in the Euclidean path as well, that it should start and end with different vertices. Start and different vertices. Okay. For the Euclidean circuit, what are the two definitions? Let me write it. Okay. So for the Euclidean circuit, the return value is 2, and what are the two definitions? So it is a Euclidean path. First of all, it is written here that the Euclidean circuit is a Euclidean path, right? So Euclidean path का definition क्या था यार? Visit exactly once. तो मैंने ये definition यहाँ पे copy कर दिया. And then we have some change that which starts and end on the same vertex. Start and end जो है वो same होंगे, और यहाँ पे different होगा. ठीक है? Okay. So your first check. So if I draw a diagram that how your code flow will look like. तो code flow कैसा होगा यार? कि first of all we will check if it is connected or not, right? So let me write it from here. First I will check if it is connected or not, right? If it is no, then I will directly say return 0. And the reason that no Euclidean path and no Euclidean circuit is possible, right? So I have to return 0. Now there's another case that the connected is there. Now what I need to check? I need to check if it is a Euclidean path or Euclidean vertex. Okay. So let us observe even more that how do we make sure that it start and end with different vertex, right? That is the second thing we need to make ensure. The first thing we need to ensure that we need to visit exactly once, right? So we have already checked it should be connected, else that is not possible. And if it is connected, like in this case 0, 1 and 2, we need to make sure that we take a path which ensures that we have visited exactly once. Okay. So I will give you one more graph. Let's say we will consider one more graph, and here the elements are, let's say 1, 2, 3 and 4, right? So you can clearly see if it have, or let's say 0 is also there. If I would have started my DFS from 0, then my path would be 0. It goes to its immediate neighbor, that is 1, immediate neighbor again, and 2 goes to its immediate neighbor, that is 3 and 4. No need to track back, right? Because मैं 4 पे आऊँगा तो मैं track back क्यों करूँगा कि इस 3 के पास और कोई neighbors बचे ही नहीं. There are no more neighbors left for 3 to visit, so I do not need to track back. ये होगा नहीं यहाँ पे, correct? And you would say that this is your path and that's it, correct? But if I add 2 more neighbors here, let's say, if I add two more neighbors, I just want to show you the case so that we can now define it. So let's say 5 and 6, right? Now if I do 5 and 6, what will happen? 4 will go to its immediate neighbor. Now there are two immediate neighbors, so let us assume it goes to 5, right? 5 pe gaya. Now, although this graph is connected, right? After going to 5, it will take, let's say, backtrack to 4. Let me show you the different color. It will track back to 4 and it will say, okay, are there another neighbors left for 4? They will say, yes, you have one neighbor, that is 6. So I will track back to, I will call the DFS for 6 again, right? And now if you see that this 4 is visited twice now, right? So what happened? After 5, after 4 it get to 5, after 5 it get to 4 again, and then it goes to 6. So 4 is coming twice in our path, right? So this is the violation of visiting exactly once. So what have been changed? What have been changed in this graph so that I would have made ensure that the edges or the vertices are visiting exactly once? Please pause this video here now. Try to think. And hint here is, try to think in terms of degree, right? Degree is nothing but the edges coming out or in. Since this is an undirected graph, so either it's coming out or like there is no directed one, right? So if 3 is here, so there are two edges connecting to it, so that means the degree here is 3, the degree here is 2, sorry, 2, right? Please try to think in terms of degree. Can you do something? And can you think of in something? So if we check if the degree should be like this, and then we can definitely make sure that if it is connected and the degree is like this, then definitely the if there would be a case jahan pe hum it is exactly visiting once. Please pause this video now here. Okay, so let me tell you, and please listen carefully, right? Please listen carefully. Okay, देखो यार, हमने क्या देखा था कि हमें देखो प्रॉब्लम कब नहीं है, when we are not having any problem. I was at 1 0, and then I went to 1, and then I went to 2, right? And I can clearly see that this is forming that we have visited 0 1 and 2 exactly once. But यही अगर if I would have given one more neighbor here, let's say 3, तब 0 से मैं 1 गया, then 1 से 2 गया, अब 2 को क्या होता है, इसको ट्रेस बैक करना पड़ता है इस 3 को विजिट करने के लिए. that means that degree of the vertices should be 2. Degree should be 2, right? Or you can say it should be even, not odd. क्योंकि अगर ये odd हो गया, then definitely you have to trace back to visit its rest of the neighbors. I hope I'm clear. Now again, if you are not clear with this particular understanding, please pause this video, reverse back and listen it again. ठीक है, तो ठीक है, इसको मैं यहाँ से रब कर देता हूँ. Great. So we have observed that the degree should be even, then we do not have any problem in moving forward, and it will automatically make ensure that we have visited that every edge just once. So now, how many degrees should be even, right? Because this 0 clearly has just one degree, right? So definitely for this degree you have odd, right? तो क्या मैं कह सकता हूँ यार कि for all the internal nodes, that is except the starting and ending point, if our graph would have like this again, 0 1 2 3 and 4, except the starting and except the ending point, for all the nodes the degree should be even. And for only the starting and ending point, because there is no other vertex attached it, we can tolerate that it is an even, right? So for except, I'm just writing it for you, except starting and ending, I can tolerate that your degree could be odd, right? Now how to check this particular thing in your code? How to check this particular thing in your code? So instead of checking all the internal nodes have degree even, it is much more easier to check the starting and ending node as degree odd. So that means I need to check the odd degrees, that the number of odd degrees should be exactly equals to 2. If that is the case, I will say this is my Euclidean path. Again, so we have covered one milestone here. You have not understood until this point, please revert back and try to listen to this understanding or the intuition again. Correct? Okay, so let us what to say, go back to the flow. Let us go back to the flow and start writing it. So it is connected. If it is no, definitely I will say no, that's not possible. And if it is yes, then I will check number of odd degree vertices, right? If it is greater than 2, right, then definitely I will say that no elliptical, or not elliptical, Euclidean path. And since no Euclidean path, this implies no Euclidean circuit, right? And here in this case also, I would say return 0. Now, again, this yes case have another, what to say, another case, that when it is exactly equals to 2, right? I'm writing the assignment operator, no, checking operator. And reason here is, here for this greater than 2, it will violates, I'll just writing it for you again, it will violate exactly one's condition given in the question. Now, if it is again equals to 2, I know that is definitely an Euclidean path. I know that is definitely an Euclidean path. And I will say, the question says if that's an Euclidean path, you have to say return 1. So I will say return 1 here, right? Great. So what is handled here? The reason here is exactly once is handled and different indexes as well. Because the graph is open. Here, right? ठीक है, अब मैं आपको बताता हूँ again the next case of Euclidean circuit. Now this particular case I have written here is can be converted to a Euclidean circuit, because the only one difference is the starting and ending point is changing, right? Let us draw the same graph and you will tell me that what the thing I would have done here, that it will follow the Euclidean path as well. We know it's a Euclidean path. Now what extra I would have done to make it a Euclidean circuit, right? So what is the ask? Ask is start and end should be same. So, and what is my current path? My current path is 1, 2, 3, 4. Now this is my start. What is my need? End should be same, right? So I will copy the same start here at the end. So after 4, I'm visiting 1. So that means there should be an edge. Pointing to my 1. Correct? Now, what you need to write in the code to handle this particular case? Now, again, think in terms of degrees, right? Here I can say that all the degrees here is even. For 1, the number of degrees 2, because there are 2 edges. For 2, the number of degrees 2, because again there are 2 edges, 1 from 2 and 3 to 2. Similarly, for 3 there are 2 edges, and 4 there are 2 edges. So all degrees are even. Now, what is easier to check? All degrees even, or there is no odd degrees? So I will check that number of odd degrees should be equals to 0. So again, let's get back to the flow, and here I will make one more case, that if it is equals to 0, then that definitely is my Euclidean circuit. And what you can say as well in the graphical representation, you say that forming a whole cycle, and this whole cycle is, they are referring with a conventional name as a circuit. And here you need to return, I'm just say writing RET2, and here you need to return 1, return 0, return 0. And I think we have covered all the aspects of this question, and I hope you were able to get a good grasp of it, right? Okay, so in summary, this is your exact crux, logic, intuition, summary, everything, right? But let me just write the code, or let me just write some of the examples here, so that you can relate it even well with the just table. So here the case is connected, definitely 1, 2 and 3. This would be the case where we need to check the connected one. Now the degree should be greater than 2. So what was the case we handled here? 1, 2, 3, 4, and at any point of time it has 2 neighbors, let's say A and B, right? So that's what we checked here. Now again, for equals to, what we checked, that at none of the nodes have the odd number of neighbors except the starting and ending point, right? We can just tolerate 2 vertices which has the odd neighbors, right? Okay, now this was the case where it was easy. So what did we see? We converted the same uppercase with the EP to EC, that is Euclidean path Euclidean circuit, and we see that starting and ending point should be same, so we just add an edge here, and then we can see that we cannot tolerate now no number of edges should be odd for any vertices, right? So everything is getting handled in this particular table. Now again, it's highly encouraged for you guys to please try in for some other examples and try to code the solution with yourself. Again, the prerequisite is DFS. So if you have faced any problem understanding this particular video, so multiple times we have used DFS, and even in the starting I've showed you DFS. So that's so very highly chance that you have not understood how the DFS run, and that is why you may have not understood the first the starting of the few minutes, right? So it is highly encouraged. So if you are like saw this video and still not getting it, start with DFS, come back to this video again and do it. And I hope it's not, I have given my best to explain you, right? And I hope you have got this thing. And again, one last thing, that if you have not yet subscribed to my channel, please like, share and subscribe so we can meet again in the tomorrow's POTD week. Chalo, let's get ahead to the coding section now. Okay, so that's the code in Java. Let me give you a very quick code walkthrough. So first we are checking if it is connected or not. For connected or not, we are just doing a DFS from any of the vertices, right? So we are starting from, let's say, 0. If it is connected, definitely this DFS will visit all the vertices, and that is what is being marked in this visited array. And now we are checking that after calling the DFS, if any of the vertices has not been visited, right, then definitely you have to say return 0. Now why I'm checking dot size greater than 0? Okay, so there may be one case, so let's say you have 1 and 2 as connected and you have not connected as 3. So DFS, starting the DFS, or let's say 0 was also there, right? So starting the DFS from 0, your visited array would look like 0 1 2 3 is marked with this one, what to say, as true, but 3 is not, 3 is marked as false, right? And in your ADJ list, the ADJ list given here is like this: 0 is connected to 1, 1 is connected to 0 and 2, and 2 is connected to 1, and 3 is also there, right? So you need to check it should be greater than 0, correct? Yeah, so this case that I was talking about is, let's say, this case. So the input given here you as, if you see in the inbuilt code, the first, the V and E is getting scanned, and then for times V we are getting a new array list, right? So that means you have V and E, and for V times the value here is 3 2, right? So for the array would be created for 3 cell, and each cell have an array list of it, right? Now what is happening, how the neighbors are getting added? So they are getting the edges, and you are saying adg of u dot add v and v dot add u, right? So that means, so this 0 and 1 is saying that 0 add 1 and this one add 0, right? So this is your first. And then for the second cell, second edge, there is 1 to 0, 1 to 0 and 0 to 1, right? And what our DFS have done is that I have called the DFS from 0, right? So 0 1 and 2, so this is marked as true, and this is as false, right? So although this is marked as false, but there are no entries here, right? So this is one of the possible cases. So that is why I'm checking if it is false and if it has neighbor, right? Yeah, so if it is false, and it has neighbors as well, so no neighbors, then also you need to check, right? So that is why we are getting a return 0 here, not connected. And then we have the second step, that is we are now counting the number of odd edges for all the vertices. So we are going for all the vertices, we are checking the number of edges. Now how we can check the number of edges? Number of edges is nothing but the number of neighbors a particular vertex has, which is stored in the adjacency list. So we are taking count plus plus if it is an odd. Now if it is greater than 2, then definitely that is violating the condition of visiting exactly once, and that is why we are checking, we are saying return 0. Now this condition is making sure that we have exactly once and different start and end, correct? So that is the count is equals to 2, so we are making sure there is an EP, that is equivalent path, and we are saying return 1. And since we have made ensure that's an equivalent path, so that's another case is for that if count is equals to 0, then definitely this is forming a whole cycle and it's a equivalent circuit, else return 2. So that is it. This is your DFS code. It's the same that we have discussed and explained in the DFS video, correct? Okay, so that is it. Let us hit the submit button. So since we are running the DFS and we are using a V space for the visited, so that means the time complexity would be the time and space complexity would be same as the DFS. So the DFS takes V plus E, so that is why V plus E is here, and O of V to store the visited vertices, right? Let us switch back to the C++ code. The same code we have seen in the dry run and in the intuition in the code as well. So that's the same. Let me just scroll it through and let us hit the submit button for this code as well. Great. So yeah, that's done. Okay, so let's just stop here now and let us meet again in the tomorrow's GFG Beauty Street. Till then, keep learning, keep going. Bye bye, and take care, guys. And do not forget to like, share, and subscribe. Bye bye.